All right, here's the example assessment on fluids. We've got 5 questions. One that just deals with density. It says, what is the mass of a 0.10 or 0.10 meter cube of steel, given that the density of steel is 8,050 kilograms per meter cubed? Okay, well, I can't answer this unless I know the volume of this cube. And a cube, which has 0.1 meters on each side, is going to have a volume of 0.1 times 0.1 times 0.1, which is 0.001 meters cubed. Well, once I know that, the rest of it's pretty easy. I'm just using density equals mass divided by volume. Now I know the volume and I know the density, so finding the mass is just going to be 8.0 kilograms. All right, when a car sinks underwater, it's possible for the inside of the car to be filled with air while the outside is water is pushing in on the car, blah, blah, blah. All that's just an interesting story. What's important is that we know the pressure of the water and we know the area of the windshield. And pressure is force divided by area. We are asked to find the force, so force is pressure times area. So it's just going to be 49,000 times 1.8, which gives us 8.8 times 10 to the 4th newtons, which is a lot of force. And that's why likely the windshield will collapse in on the car and flood the car with water. All right, for this problem, assume ideal flow. That means we're going to be using 2 equations. V1A1 equals V2A2, and pressure 1 plus rho GH1 plus 1/2 rho V1 squared equals pressure 2 ... We should know the rest of that formula. Those are the 2 equations we're going to be using. What's the speed of the water in the fatter section of the pipe? Okay, let's see what we know. For this problem, assume ideal flow. A level. What does that mean? That means that the pipe does not go uphill. So, boy, that's a terrible picture. So we've got this pipe which starts out fat and ends up thin, but it does not go uphill. So that means my H1 and my H2 are going to be 0. So that phrase, level, tells me that it's not going uphill. So the height's not changing. Okay, the pipe has a radius of 0.5 at one end. Okay, we'll call this end number 1. We'll call that end number 2. 1 is the fat end. 2 is the skinny end. We measure water moving at 4.5 meters per second with a pressure of 1,500 or 150,000 pascals at the thinner section. So that means that V2 is equal to 4.5 meters per second, and pressure 2 is equal to 150,000 pascals. All right. We expect pressure 1 to be bigger because the slow-moving water should have higher pressure. We also expect velocity 1 to be slower. Okay. Let's see. And I guess we know that R2 is equal to 0.03 meters and R1 is 0.05 meters. Okay, so for part A, we're going to use this first equation, and we know A1 pi r squared. We know A2 pi r squared for the other radius, and we know velocity 2. So this is going to say that velocity 1 is equal to velocity 2 times pi r2 squared divided by pi r1 squared. My pi's cancel. Velocity 2 is 4.5. Radius 2 is 0.3. 0.03. Radius 1 is 0.05. So when I plug in my numbers, I get that it's moving at 1.62 meters per second in the fat part of the pipe. It's moving slower, which makes sense. What's the water pressure at the fat part of the pipe? Okay, so that's asking me to find P1. So P1 should equal P2 plus 1/2 rho V2 squared plus rho GH2 minus 1/2 rho V1 squared minus rho GH1. So I plug in my numbers, 150,000 plus 0.5 times 1,000 times 4.5 squared. Okay, and H2 is 0 and H1 is 0, so minus 0.5 times 1,000 times 1.62 squared, and I get 158,813 pascals. Two significant digits means that I get 1.6 times 10 to the 5th pascals. We went from 1.5 times 10 to the 5th to 1.6 times 10 to the 5th. The pressure went up by about 10,000 pascals. Okay. Number 4, assume viscous laminar flow. So we're going to be using Q equals the pressure difference times pi times r to the 4th divided by 8 times the viscosity times the length of the pipe. Okay, for this problem, assume viscous laminar flow. Air density is 1.2. Viscosity is 1.983 times 10 to the minus 5. It's traveling through the ducts. The duct is 10.5 meters long and has a diameter of 2.1 meters. What is the pressure drop if there's 0.61 meters cubed of air flowing through the duct? Okay, so I need to rearrange this for pressure drop. Pressure drop is equal to 8 eta L Q divided by pi r to the 4th. So that is 8 times 1.983 times 10 to the minus 5 times 10.5 times Q 0.61 divided by pi times r. Now r is 0.105 because d, the diameter, is 2.21, so I need half of that raised to the 4th power. And what I get is a pressure difference of 2.66 pascals, two significant digits, 2.7 pascals of pressure, which is very little, but that sort of makes sense. It doesn't take much pressure to push air through a pipe. From the problem above, calculate the Reynolds number. Okay, so the Reynolds number is the density times velocity times diameter divided by viscosity. Okay, the density of the air is 1.2. The velocity of the air is, we don't know. Okay, Q is velocity times area. So we know Q, and we can figure out the area as pi r squared. So Q is velocity times pi r squared. So that means my velocity is equal to my Q, 0.61, divided by pi times radius, 0.105 squared. So my velocity of the air is 17.6 meters per second. Okay, so now I can figure out my Reynolds number. I'll take that velocity times my density, 1.2, times the diameter of my pipe, 21, divided by the viscosity of air, 1.983 times 10 to the minus 5. And we get a Reynolds number of 223,800 approximately, which of course is way above 2,000, so not laminar. Okay, not laminar. And what is the Reynolds number? How many significant digits should I be using? Looks like 2 significant digits, so that is 2.2 times 10 to the 5th. Not laminar. And that's the end of the practice quiz. Okay, so hopefully that was helpful, and good luck.